This is part one of radical expressions and rational exponents. By the end of class today, you'll be able to rewrite complex radical expressions by using rational exponents and evaluating the expressions containing rational exponents. Let's start this off right with a little bit of a joke. How is an artificial tree like the fourth root of negative 68? Wait for it. Wait for it. There it is. Neither has real roots. Ho ho. Ho ho, holy mackerel. Okay. If you haven't done this, please pause the video here. Otherwise, let us begin. So in this warm-up, we're going over some of the exponent rules. You should be pretty good at these by now. If you have two bases are the same, like you do in number one, you're able to combine the exponents by adding. So you would end up with 7 to the 5th. On number two, if you have two like bases, where one's in the numerator and one's in the denominator, you can apply the quotient rule to subtract the exponents. What does that look like? Well, if you want to move the 11 to the 6th to the numerator, you subtract the 6. I could rewrite this as 11 to the 8th minus 6, which ends up giving us 11 to the 2nd power. Now, if you write it as 11 to the 2nd power, I know obviously you understand the exponent rules, but you should also know what 11 squared is. So I would expect you to write this as 121. Now over here it's a little bit different. This is not the same rule we did in number 1 or number 2. This is the power to a power rule, which means instead of adding exponents or subtracting, in this case, you're going to multiply the power being raised to a power. So that would be 3 times 2, which is rewritten as 3 to the 6th power. Now, another reason to think about why this rule exists, when you think about taking everything in parentheses to the 3rd power, it really means you're taking 3 squared times 3 squared times 3 squared. You're doing it 3 times. And if you use the rule from number 1, you would end up adding the exponents and you'd still get 3 to the 6th. 3 to the 6th is a pretty big number. If you leave it as 3 to the 6th, I'll call it good. Number 4 is reducing radicals. Since this is a square root, you're going to want to find perfect squares that would go into 75. Perfect squares being things like 4, 9, 16, 25, 36, 49, and so forth. In this case, 25 goes into it, 25 goes in. So you can write this as the square root of 25 times the square root of 5. And the whole reason we picked a perfect square is because we actually know what the square root of a perfect square is. The square root of 25 is 5. So this becomes 5 square roots of 5. Now, the next one, there's a couple things going on. You look at the square root of 20, and there are perfect squares that go into it. You look at the square root of 7 in the denominator, and you should think to yourself, man, I really need to rationalize this denominator. Before you go rationalizing the denominator, it's always prudent to try to simplify everything first, even if it's an easier problem like this. So let's figure out what perfect square can be used to factor out the 20. Well, the biggest perfect square that goes into 20 is 4. So you could rewrite this whole thing as the square root of 4 times the square root of 5 all over the square root of 7. Keep going. The square root of 4 is 2. So this is 2 square roots of 5 all over the square root of 7. Now it's going to make sense to try to rationalize the denominator. Remember, our goal is to get rid of the square root or any radical sign in the denominator. So I'm going to multiply by the square root of 7 over the square root of 7. Our goal was to get rid of the radical sign in the denominator. We've done that successfully because the square root of 7 times the square root of 7 is just a 7. And when you multiply, you can only multiply like terms. So in this case, you're going to take the square root of 5 times the square root of 7, which is the square root of 35. And don't forget about that 2 that's still there. Now, there are no perfect squares going to 35, so you're done. On the next one, I'd suggest doing a couple of things. There is a really slick way to get this one, but let's do the long way just in case you're more process-oriented. I can rewrite this as the square root of 15 times x, because the square root of x squared is just x all over the square root of 3. Now I'm going to rationalize the denominator. When you multiply these, you're going to end up getting 3, and then you're going to have to take the square root of 3 times the square root of 15, which gives you the square root of 45, and then you still have an x outside of the radical. Let's try to simplify 45, the square root of 45. We're going to look for the biggest perfect square that goes into that. That would be 9. So in this case, I can rewrite the square root of 45 as the square root of 9 times the square root of 5 times x all over 3. Keep going. The square root of 9 is actually 3. Since you have a 3 in the numerator and the denominator, they all cancel, and your final answer should be x times the square root of 5. I would always list the radical term second. That's traditional mathematical notation. It's not wrong if you put the square root of 5 in front. It just makes it more likely that you'll make a mistake. Okay, let's get into the lesson. What is a rational exponent? Well, it's an exponent that can be expressed as a fraction, where m and n are integers and n is non-zero. So it is an exponent that can be expressed as the fraction m over n, where m and n do not equal 0. So when you say rational exponent, here's what they really mean. The word rational refers to anything that can be written as a fraction with integers. So you see m over n here, it's a fraction, and these have to be integers. If they can be written that way, that's what makes them rational. The exponent part is m over n is going to be an exponent, as you'll see down below. And of course, they cannot be equal to 0 because that wouldn't make sense. Okay, so let's go over to the definition. A raised to the exponent. Now we're talking about an exponent that's a fraction. If you have an exponent, you can always rewrite it in radical form. In this example, the denominator of the exponent turns into the index of the radical. And then the base turns into the radicand. A much more generalized formula, and one I like a lot better, is it shows the exponent in both its numerator and its denominator. So in this case, n, the denominator, is still going to be the index of the radical. The numerator, the top part, ends up being the power, the thing you're raising the whole radical to. Now, I want to point out that this is one way to rewrite the exponent a to the m over n power. You can also switch the order of operations. So, in example number 1, you're doing the radical first and then doing the power second. Well, you could also write it where you do the power first and then you do the radical second. Both of these are equal. And you're going to notice when you go through problems that sometimes you're going to want to choose which one you want to use based on which one's going to be easier. So let's do an example. I really encourage you to pause and try to do A. When you're done, just hit play. So the rule says that the denominator is the index. The numerator is the power. So I'm going to rewrite this, but one thing I want you to be real careful about is that only 32 is being raised to that exponent. The negative is just in front. You don't mess with the negative, it just stays there and will be there the whole problem. So I'm going to rewrite this, negative's out front, but it's now going to be the 5th root, that's my index, of 32 raised to the 3rd power. I wrote that correctly. But notice something that might be problematic. Like, for example, figuring out what 32 to the 3rd power is. Kind of a big number. Then I got to take the 5th root of that. Kind of hard. So, maybe this would be easier if I rewrote it the other way. If I wrote it as negative, and then I said it was the 5th root of 32, all raised to the 3rd power. Now I have something that's much, much more manageable. So, for example, you know that 2 to the 5th power is 32, which means the 5th root of 32 is just 2. And then it's going to be a lot easier. So I'm going to rewrite this as negative. Then I'm going to have a 2 in parentheses, because that's what the 5th root of 32 is, raised to the 3rd power. Now you can keep going, because I'm pretty sure you can figure out what 2 times 2 times 2 is. Final answer is negative 8. All right, let's look at 6. Let's go ahead and rewrite this. Since the index is 2, that's just an old-fashioned square root, index of 2. So it's going to be the square root of 6 to the 3rd power. Now, I don't really know what 6 to the 3rd power is off the top of my head, but I can certainly pull my calculator out and write it down. So I'm going to take 6 times 6 times 6. When I do that, I get 216. So now I'm trying to figure out the square root of 216. Now, I don't immediately know what perfect squares go into 216. Remember, that is index 2, so I'm looking for perfect squares. But I can certainly write them down and start dividing this thing out. So, for example, a pretty big perfect square I know is 225. That's 15 squared. Well, there's no way 225 is going into 216. I got to find smaller numbers. So I'm just going to try some. Maybe I'll try 81. 216 divided by 81 didn't work. I'll go down one. I'll go to 8 squared. So 216 divided by 64 didn't work. 216 divided by, 49. And didn't work. 216 divided by 6. Oh, wait. That worked. Of course it worked. This is 6 cubed. So if I divide by 6, it's going to work. Or if I divide by 36, it's going to work. So I could have rewritten this thing as the square root of 6 squared times 6. Right? I could have done that because 6 cubed is the same thing as 6 squared times 6. Well, let's write it this way. The square root of 6 squared times the square root of 6. Well, the square root of something being squared is just 6 times the square root of 6. Final answer. Now, if you get thrown off sometimes when you see the square root of 6 squared and you wonder what it is, you could write this as exponential form. So, for example, 6 squared raised to the 1/2 power is the same thing as the square root of 6 squared. Well, if you use your power to a power rule where you multiply 1/2 times 2, 1/2 times 2 is 6 to the first power. That's another way to think about where this 6 over here came from when you evaluated this. (64 to the third power). Writing in that radical form, that's our index, so it's third root of 64. Now, third roots would be things like 2 to the third power, so that'd be 8. Another third root might be 3 to the third power, that's 27. Let's see, I don't think 27 goes into 64, so let's try to the fourth power. So again, I'm going over all the perfect cubes because perfect cubes allow you to rewrite this. So 2 cubed equals 8. 3 cubed equals 27. 4 cubed equals 64. That means the third root of 64 is just 4. Four raised to the 5/2 power. I can rewrite this. This is my index, so that's just an old-fashioned square root. So I've got the square root of 4 to the 5th power. There are a couple different ways to think about this problem. You could take 4 to the 5th power and get some ginormous number and then try to find perfect squares that go into it. Or you could get a little bit more tricky. So for example, you can rewrite 4 to the 5th in expanded form. I could write this as the square root of 4 times 4 times 4 times 4 times 4. And using the product rule, I can separate all these, or the radical rule. It'd be the square root of 4 times 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 the square root of 4. And when you do that, each one of these is 2, which gives you 32. So sometimes think about how you can find a perfect square if you're looking at an index of 2 in something like 4 to the 5th